We'll begin our Mastering Physics assignment here. So for this first one, we have a basic kinematics problem. So I'm first going to set up my chart here. So I have the speed skater initially traveling at 8.8 meters per second. They're going to slow down over a distance of 5.5 meters to a final velocity here of 6.5 meters per second. So we want to solve for our acceleration in this case, so I'm going to use my VF squared equation. So we have VF squared equals VI squared plus 2A delta x, so 6.5 squared equals 8.8 squared plus 2 times A times 5.5. I can go ahead and simplify this sum, so 42.25 equals 77.44 plus 11a. When I go ahead and I solve for a, I get an answer here of negative 3.2 meters per second squared. And that would be correct to 2 sig figs. Moving on to our next problem here, we're once again going to set up our chart and think about what things we know. So we're accelerating from rest, which means our initial velocity is 0, to a speed of 4.5 meters per second in a time of 0.15 seconds. And the first thing we're asked to calculate is the acceleration. We actually have two formulas. I'm just going to do the VF equals VI plus AT, but we can use our formula from before for acceleration. So I have 4.5 equals 0 plus A times 0.15. I divide both sides by 0.15 to get an answer of 30 meters per second squared. The second part asks for how far it moves during this time. So I'm going to use one of my delta x equations. I'm just going to use this one, but there are a few options for which one you want to use. So I go ahead and plug in the things that I know, and I solve for delta x, and I find that delta x is equal to 0.34 when I round to 2 sig figs meters. Is actually 3375, but 3.4 if we're rounded to 2 sig figs, as the question asks. All right, moving on to this next one. This one's a little bit more complicated here because we have a situation, we have a person running, and they're running with one acceleration in the beginning as they speed up, and then maintaining that speed, meaning 0 acceleration, until the finish line. So what we're going to do is we're going to split this up into two charts. We're going to have one for while we're speeding up and one for while we're traveling at a constant, and we're going to just take it one step at a time. So for the speeding up portion, we are starting from rest and reaching a final velocity here of 11 meters per second over a time of 2.84 seconds. Okay. For the constant portion, we're traveling at a constant speed of 11 meters per second because that's how fast we're going at the end of this interval. So it's going to become our initial velocity for the next one. And it's also going to be our final because we're traveling at a constant speed. So it's not going to change, and that means our acceleration is 0. Now, there is this piece about 100 meters, okay? Be careful, though, because neither distance that we have here is going to be the 100. 100 is the total amount of distance that we run, so it's going to be the combination of these two. So we don't actually know it yet, but that is something important to keep in the back of our mind. So what I'm going to do is I'm actually going to start off with my speeding up portion because I see I have 1, 2, 3 pieces of information, and I'm going to go ahead and actually calculate that delta x. Okay, I know that's a useful piece of information because it links the speeding up portion to the other side. So we're going to go ahead and calculate that and see where we can go from there. I'm going to start with that delta x equation based off of what we know and plug in the things we have. So we know our final is 11, our initial is 0, our time is 2.84. So when I end up calculating that, I get that during the speeding up portion, the runner traveled 15.62 meters, which means that this delta x here, okay, is going to be 100 minus 15.62. Okay, the remaining distance, the remainder of that 100 is going to be traveled at a constant speed. So my delta x for the constant speed portion is going to be 84.38. Okay. And now that I have that, I can go ahead and solve for my time. So once again, I'm going to actually use that exact same equation. We do have other ways of doing this that don't involve using the same equation over and over again, but this is probably the easiest way actually for this particular problem. So what I end up getting is 84.38 is equal to 11t, and then when I divide by 11 to get my time here, I get that my time is going to be 7.67 seconds. So what is my total time? Keep in mind we need to combine both of these times to get that total time, but when we do that, we get an answer here of 10.51. Alright, once again we have a situation where there's multiple accelerations. So we have this car speeding up for some period of time, maintaining a constant speed for some period of time, and then slowing down. So I'm actually going to have 3 charts here that I'm going to set up. So starting with that first portion, that's where we have a car starting from rest, so 0 initial velocity, and accelerating at 2 meters per second squared. Right, over a period of time of 5.7 seconds. We then maintain a constant speed, so I know my acceleration is 0 for that period of time for 3 seconds. That's what that coasting piece means. And then we slow down at a rate of 1.5 meters per second squared to get to that next stop sign. So we're going at some speed, slowing down at 1.5 meters per second squared. I know my final velocity is going to be 0. So let's start analyzing this one piece at a time. I'm going to start with part 1, and I'm just going to find everything that I can find and then go from there. First thing I'm going to find is my displacement. We are ultimately looking for how far we go. So I'm going to find that right off the bat. So I'm going to use my delta x equation there. And so what I end up getting is delta x is equal to 0 times that 5.7 plus 1/2 times 2 times 5.7 squared. So my displacement for the first portion, maybe we'll call it delta x1, is 32.49 meters. The other thing I can find is my velocity for that point, that final velocity, using my VF equation. And so VF is going to be 0 plus 2 times 5.7, which means my final velocity is going to be 11.4 meters per second. So we found the displacement of the first part. We also found something that's really valuable, and that is the final velocity for the first part becomes the initial velocity for the second part. So I now know my initial velocity for the second part, and since we're maintaining a constant speed here, not accelerating, I also know my final velocity. And that means I can go ahead and find my displacement here for that second part. So I'm going to use that delta x equation there. Keep in mind that the delta x equation is the only useful equation when we have 0 acceleration, or one of the 2 delta x equations, I should say. You can't use any of the other ones when you have 0 acceleration. So I go ahead and solve for that, and I find that my delta x here is going to be 34.2 meters, delta x2. Moving on to my last one, I know that the final velocity for that last one becomes the second to last one becomes the initial velocity for the last one, right? At the end of that constant interval, I'm still traveling at 11.4 meters per second. And so the initial velocity when I begin to slow down is 11.4 meters per second. And now I'm going to be able to go ahead and solve for displacement. So I go ahead and I'm going to use my VF squared equation. And so I have 0 equals 11.4 squared plus 2 times -3 times delta x. So we have 0 equals 129.96 minus 3 delta x. And that means that my displacement for that final portion is 43.32 meters. I'm now going to go ahead and simply add up all my displacements, 32.49 plus 34.2 plus 43.32. And that gives me a total answer of 110 and 0.01, but we want to round to 2 sig figs, so just 110 meters. Moving on to our next one, we have a car now traveling at a speed of v, and it's slowing down to a stop over a distance of d. And we want to know what would happen if the car was traveling at a speed of 8v instead. All right, how long would it take to stop? So this is one where we want to set up two things, our original situation and our new situation. So for our original situation here, initially we're traveling at a speed of v, we are slowing to a stop, so our final velocity is 0, and that occurs over a distance of d. All right. For our new situation, we now have a velocity of 8v. We're still slowing to a stop, and we're searching now for this new distance. I'm going to call it d prime. Okay. There is one other really key piece of information, and that's this line here. Assume the acceleration is the same in both cases. So that means that I can make that acceleration be the same variable. So I'm just going to call it a, and I'm going to make it a negative a actually, because I know that I'm slowing down. So I'm going to go ahead and set up an equation for each one. We don't know time, don't care about time, so I'm going to use the VF squared equation for both of them. So for the original situation, we're going to have 0 squared equals v squared plus 2 times negative a d, which means we get 0 equals v squared minus 2ad, or v squared equals 2ad. For the new situation, same equation. So we have 0 squared equals 8v, that quantity squared, plus 2 times negative a times d prime. Keep in mind that we need to square that 8 there. All right, whenever we have that coefficient in front, you have to square that coefficient as well. So we actually get 64v squared minus 2ad, or 0 equals 64v squared minus 2ad. So 64v squared equals 2ad prime. So I'm going to go ahead and combine these equations, and what I see here is that there's a v squared there and a v squared there, so I can actually just substitute in. So we can say 64 times 2ad is going to be equal to 2ad prime. The 2 and the a will actually divide out here. So what we end up getting is 64d equals d prime. So our answer here would simply just be 64, because it asks for it in terms of d. Moving on here, we have another kinematics problem. Ball bearings in free fall here, so I'm going to go ahead and set up my chart. So we know that the ball bearings are in free fall for 4 seconds, so that's my time. They're also being dropped, which means that initially they're not moving, right? Anytime something is dropped, it has no velocity in the beginning. And they're accelerating, of course, at negative 9.8 meters per second squared. So first we want to find out how high our tower is, okay? So that really is going to be asking for how far do they fall, which would be their displacement. So I'm going to go ahead and solve for that. We know our initial velocity is 0. We know our acceleration, and so we can find that displacement using our delta x equation. So I solve for it, I end up getting an answer of negative 78.4 meters. So that is our displacement. We are losing height, we are dropping. However, the question asks, how high is the tower, not what is our displacement. It doesn't really make sense to say the tower is negative 78.4 meters tall. So I'm going to say the height of our tower is simply 78.4, and I'm going to round that to 2 sig figs, so just 78 meters. For the second part, we want to know what our impact velocity is. That would be the velocity when it lands. So we're going to go ahead and solve for VF. So I'm going to use my VF equation here. So we have V final equals 0 plus negative 9.8 times 4. I go ahead and solve for that, and I get negative 39.2 meters per second. It does ask us to assume that positive is directed upwards. All right, so this one directed downwards should be negative, and we do want to round it to 2 sig figs though, so I'm just going to say negative 39 meters per second. Moving on to our next one, we have another free fall problem here with a football being kicked straight up in the air. And we know that it hits the ground 4.6 seconds after it was kicked. So I'm going to start out actually by drawing our diagram here of the motion of the ball as it flies through the air. I think that's always helpful for problems like this. And I'm going to fill in all the things that I know conceptually before I start to do this. So I know that the time here at the end is 4.6 seconds, and since it is symmetrical, landing back on the ground, the time at the peak is half of that, 2.3 seconds. I also know the velocity at the peak is 0, and my displacement when I return to the ground is 0. So we have here 4 solid concepts that we know, 2 that occur at the peak here, 2 that occur when it returns to the ground. And we're going to be able to use those to analyze this situation. So this first question asks us to find the greatest height reached by the ball. So I'm going to think about this portion of the flight from the ground up to the peak and go ahead and set up my chart based on that. So for that portion, I know that my final velocity is 0. I know my acceleration is negative 9.8 meters per second squared because it's in free fall. And I know that my time to the peak is 2.3 seconds. So I'm going to go ahead and solve for some things. I actually need to find my initial velocity first, and then I'll be able to find my displacement. So to get that initial velocity, I'm just going to use my VF equation. So with that, we have 0 equals VI minus 9.8 times my time, which is 2.3 seconds. And I'm getting an initial velocity here of 22.5 meters per second. So that actually answers question 2. We just went around to 2 sig figs, making it 23 meters per second. Okay. Now that I have that, I can go back to answering part A, which is finding my displacement as I rise up to the maximum height. You have a few options here now of what equation you use. I'm just going to use the delta x equation, but there certainly are other choices. So we'll fill in the things we know. That initial velocity is 22.5 times our time of 2.3 plus 1/2 times negative 9.8 times 2.3 squared. I can go ahead then and solve for my displacement. So I end up getting the displacement here, which is my max height of 25.92 meters, which rounds, if we're doing 2 sig figs, to 26 meters. So we have another free fall one here. So I'm going to start by drawing that diagram of the object flying through the air, and then we'll go from there. So we have a ball here that is thrown up in the air, and we're told that it's thrown from a hand that's initially 2 meters above the ground. And so that ball is going to go up, rise up to the peak, and then fall back down all the way to the ground. Okay. We know that it's thrown with an initial velocity here of 15 meters per second. We know our velocity at the peak is 0, of course, and that's about all we know. We also do know our displacement at the bottom. So I'm going to start with that, and I'm going to set up our chart here. So the things I know that initial velocity is 15 meters per second. My acceleration is negative 9.8 meters per second squared. And my displacement, going from the very beginning, right here, to the very end, is negative 2 meters, because I land 2 meters below where I started. So I'm going to go ahead now and use that information to solve for time. So if you do use the delta x equation, you will get a quadratic, and that's perfectly acceptable. What I'm going to do, though, is I'm actually going to use my VF squared equation. So this is the quadratic trick here. And I'm going to use that VF squared equation to get my final velocity first, and then I'll be able to go ahead and solve for my time. So with that, we have VF squared equals 15 squared plus 2 times negative 9.8 times negative 2. It's important we're careful with our signs here. If we're not, we will get the wrong answer. So when I end up solving that for VF, well, I find that VF squared is 264.2, so my final velocity then is 16.25. But keep in mind, the way we got this was by taking the square root of both sides here. And so we ended up taking the square root of something squared, which means we need to add a plus or a minus here to our answer. In this case, we know our object is going down, so it's going to be that minus. Once I have that final velocity, I can go ahead and use that VF equation to solve for my time. So negative 16.25 equals 15 minus 9.8 t. So we have negative 31.25 is equal to negative 9.8 t. And when I solve for time there, I end up getting a time here of 3.19 seconds. It does ask us to round to 2 sig figs, so that becomes 3.2 seconds. Moving on to our final problem here, we have two stones being thrown downward, and we know that the one stone or the two stones hit the water below and create a splash at the exact same time. So we're going to be setting up two situations, one for stone 1, one for stone 2. So I'm going to start by doing my chart for stone 1 here because we know the most information about that. So for that first stone, we know it drops 60 meters. It's initially thrown down at a speed here of 1.5 meters per second. It tells us that in the beginning of the problem. So that initial velocity is to be negative 1.5 meters per second. And our acceleration is negative 9.8 meters per second squared. And we're once again looking for time. Okay, so I'm going to do the same thing I did in the last problem. I could go ahead and find time directly, but that would require the quadratic, so I'm going to first solve for my final velocity. So we're going to end up with VF squared equals 1.5 squared plus 2 times negative 9.8 times negative 60. So I end up getting that VF squared is equal to 1178.3. So then my final velocity is going to be 34.3 meters per second. Once again, we need to do our sign check here and think about the fact that that velocity is going to be negative because it's going down. Once I have that final velocity, I can now solve for my time. So I can say negative 34.3 equals negative 1.5 minus 9.8 t. You could have, by the way, from the very start, just said that your everything down was the positive direction, and then you wouldn't have to worry about all these negative signs. But we're already doing it, so what's the harm? So we end up getting negative 32.8 equals negative 9.8 t, and so our time becomes 3.35 seconds. Rounded to sig figs, this becomes 3.4 seconds. Moving on to part B, we're now dealing with the second stone, so I'm going to set up my chart for that. So the things that we know this one also drops a distance of 60 meters. We don't know the initial velocity. The acceleration is still negative 9.8 meters per second squared. And our time, we actually do know. So we know that our time for the first rock is 3.35, and this one is thrown 1 second later. So I'm just going to say it's 3.35 minus 1, or 2.35 seconds. So now I have enough to work with, and I can calculate the first thing that I'm asked to calculate, which is the initial velocity of that rock. So I go ahead and plug in what I know here. So I have negative 60 equals VI times that 2.35 plus 1/2 times negative 9.8 times that 2.35 squared. So I do a little bit of math here to simplify, and I end up with negative 34.08 equals VI times 2.35, which means that initial velocity is going to be negative 14.5 meters per second. We're going to round it, and it asks for a speed, so we'll make it positive, and therefore it becomes 15 meters per second. Moving on to part C. For that, we want to find the speed of the stone, of the first stone as it hits the water, and we actually already did that here in our first part. So for part C, we're just going to use that answer, that negative 34.3 meters per second. It's just going to become positive because once again we're asking for speed, and we're going to round to 2 sig figs to get that 34 meters per second. For the last part, we're trying to calculate the speed of the second stone as it hits the ground, and so we're once again going to turn to our VF squared equation to help us find that final velocity. So we have VF squared equals that negative 14.5 squared plus 2 times 9.8 times negative 60. So we end up finding the VF squared is equal to 1386.25. So our final velocity is going to be 37.2, and it would be negative if we're talking about our velocity. However, it's going to round to a positive 37 meters per second when we consider the fact that we're looking for speed and we want to answer to 2 sig figs.